Welcome back, everyone. Our next speaker is Martin. Martin is a solution architect, an IT consultant, and a Java enthusiast. He leads the Bulgarian Java User group and organizes J Prime conference. In his talk, Martin will explore the art of static code analysis, demonstrating how to build a powerful code analysis tool. He'll be showing it with Java frameworks like Eclipse JDT and JavaParser. Ladies and gentlemen, give a warm welcome to Martin Toshev.
Thank you. Thank you very much for the great introduction. And just before we start, I'd like to ask you very quickly, how many of you have used some tool for static code analysis, something like SonarQube or other tools similar? Okay, most of you. So in this session, I'm going to try to show you how you can build a tool similar to SonarQube or something even better of your own. But just before we start, a few short words about me. So my name is Martin, as he already introduced me. I'm currently a solution architect at the European Patent Office, and I'm also one of the guys that helps run the events of the Bulgarian Java User group. And I also have a book about RabbitMQ if you're interested in that topic. So let's first look at the landscape of why we need static analysis. Why is it becoming even more popular nowadays? There are multiple reasons why I would like to use static analysis. You would like to calculate some source code metrics, like lines of code or more complex ones. You would like to find some bugs in your source code that are discoverable via static analysis. You might also use static analysis for vulnerability scanning. You can search for well-known vulnerabilities in your code base. You can also do things like automated refactoring, what pretty much many of the modern development IDEs do, like Eclipse, IntelliJ, other famous IDEs. You can do even more advanced things like, for example, code completion. So you might have certain code that's not really compiling, and you can use static analysis even to try to complete that source code. And you can also use static analysis, last but not least, to enforce source code or quality standards. There are frameworks like, for example, ArcUnit in the Java space, which are gaining more popularity, and they allow you pretty much to write tests that validate that your source code repository follows certain structure. You have proper naming, you structure code in proper packages, and so on and so forth. So these are just a few of the reasons that you might choose to write or use a tool for static code analysis. Now, to perform static code analysis, we need to have proper representation of our source code. In older days, people tend to write their own parsers for the particular language, whether it's Java or any other language. There weren't that many tools or frameworks that you can use to parse the source code, build some proper model for that source code, and analyze it. And typically, a programming language can be described by a formal grammar. A parser typically generates proper representation of the source code based on a formal grammar. However, we can have different types of formal grammars. The most basic form of parsing that you can use are regular expressions, for example, which allow you to use regular grammars to parse the source code. Many of you have used, I guess, in some form regular expressions in your daily work. However, the main inconvenience is that regular grammars are not very easy to use, especially for modern programming languages. That is why the most common format used to represent source code structure is the Backus-Naur form, or variants of it, like the extended Backus-Naur form. And there are also other types of formal grammars, like, for example, PEC grammars. So regular expressions is the first thing that you can try to use if you want to build your own parser, and they are available in most popular programming languages. However, they are really mostly used for basic text parsing tasks, not really to analyze programming languages. They are really not suitable to parse especially more complex structures available in the programming language. And not only that, they are in many cases hard to maintain and slow. So that's why one of the most well-known formats used to parse programming languages is the Backus-Nuller form, as I mentioned. It's based on context-free grammar rules, and a parser can also be generated. So in recent years, it became popular that we don't write the parser on our own, but using specific rules, we can use a framework like Antler or JavaCC to generate a parser that we can use to parse and analyze further our source code. Now, parser generators look like this. So we have a grammar. For example, we have a grammar file that describes the structure of our language. And we put that grammar as an input to the parser generator. When the parser generator, on behalf of that grammar, generates a parser. And that parser is pretty much an application that we feed as an input our source code. And the parser may generate either a parse tree, which is a convenient structure, data structure that we can use to analyze our source code, or with some more analysis, the parser can also generate an AST, or abstract syntax tree. So the abstract syntax tree is a more compact form of the parse tree that we can use to analyze our source code. In practice, this looks like this. For example, we have a very simple grammar that allows us to parse expressions like addition, multiplication, and so on. We feed that very simple grammar to Antler, for example, or it can be another parser generator that supports this format. This generates on a parse tree, which, for example, if we have a very simple line of input like x multiplied by 10, the parser, when we pass this to the parser, generates a parse tree which looks like this. At the root, we have the expression. We have an expression node, which has another child node, which is multiplication, which has left and right branch, which is x and 10. However, this parse tree requires more effort if we want to walk through it or analyze the source code based on that. So that's why most parser generators eliminate some of the additional nodes that we have and generate a more compact abstract syntax tree, which we can see on the diagram below. We have multiplication node with the left and the right node, which is x and 10. So this is like a more compact model that we can use to analyze our source code. In Antler, for example, grammars are represented using the extended Backus-Nuller form. Antler, one of the main benefits is that it has a lot of ready-to-use grammars for many programming languages. It provides the possibility to generate listeners, visitors that can be used on the parse tree, meaning that we can pretty much listen for different types of events during the parsing of the source code and act upon those events. For example, we can extract source code metrics or do some other activities like look for potential issues in the source code and so on and so forth. Has any one of you used Antler in a project? Not many people. Okay. So to generate a Java lexer and a parser for a grammar using Antler 4, which is the latest version of the Antler parser generator, what you can do in your project, you can create the grammar files if, let's say, you have a standard Java Maven project, for example. You put the grammar files under source main Antler 4 directory. You add a proper dependency and plugin for Maven for Antler. And then you run your application to generate the lexer and the parser using your standard Maven build. This is typically the process of how you can generate a parser using Antler, and we'll see it in a few moments. Another alternative to Antler is JavaCC. It originates from a parser generator called Jack at the time of Sun Microsystems. The grammar in JavaCC is also represented as extended Backus-Nuller form. However, it provides parser generation only in Java. Antler, as we said, is a general-purpose parser generator that allows us to generate parsers for multiple programming languages, while JavaCC is targeted entirely for Java. It has less features than Antler. It is easier to use and more intuitive for Java developers because in the grammar itself that we define, we can also put some additional Java logic. So you can think that in JavaCC, the grammar is some kind of a mixture of Java source code and the grammar rule definitions. Here is how a grammar in JavaCC looks like. We have a preprocessor, which says parser begin. We define a class with the main method that initializes the parser. When we say parser input is the root rule in the grammar that allows us to start the generation of the parser. And after this processor, we define the grammar rules. We define that our input is some kind of an expression, and so on and so forth. So as you can see, it's not really the nicest thing on the planet, because Antler, it really generates the parser based entirely on grammar rules. And here in JavaCC, we can do more things, because we can put Java code in the grammar definition, but it's like we mix grammar rules and source code in the same file. So to generate a Java lexer and parser for a grammar with JavaCC, you can do something similar like you do with Antler. You create the grammar file under source main JavaCC folder by default. You add a JavaCC dependency and plugin in Maven and Gradle build file. You generate lexer and parser using Maven or Gradle build. And there are also some additional extensions for JavaCC, like JJ3, which allow you to insert more build actions, allow you to extend the capability of the parser generator. And there are other formal grammars that can be used. So as I mentioned earlier, we also have some libraries that are based on the parsing expression grammar. It's a popular alternative to context-free grammars. A popular library in Java that you can use to write PEC-based grammars is parboiled. I would say it's simpler to use because you define the grammar rules in the source code. You don't need a separate file with the grammar rules, with the grammar definitions. And PEC grammars look very similar to context-free grammars. This is how it looks. So to define a grammar, we need to define a class, in that case called expression parser. We annotate that with a special parboiled annotation called build parse3. And inside that class, we define methods that define the rules of our PEC grammar. Our root rule or the input rule is a sequence of expressions. Each expression might be a term, one or more plus minus characters. A term on behalf of that can be a number, and one or more multiplication or division signs, then another number. A number is one or more digits, and so on. So this is a very simple grammar that allows us to write numerical expressions, for example. And to initialize that grammar, so we create an expression parser we call parboiled create parser. We read from the standard input the source code that we supply to that parser. And then what we can do with the library is we can print the parse tree that is generated or attach some logic so that we can do some analysis on the parse tree that parboiled generates for us. It's very hard if you want to write a custom parser. So typically that's a hard and non-trivial task. It's even harder to parse a modern programming language like Java, Python, and so on. And for that reason, it's either easier to use a parser generator like the ones that we saw earlier, like Antler or JavaCC, or use an up-to-date language-specific Java parsing library. So if you use a specific programming language, it might be even better to look up a library that already provides you with an easy way to parse programming language and use the utilities provided by that library than using a general-purpose parser generator like Antler. Now, let's see a bit how parser generators work. So, I have a first thing, if I want to use, for example, Antler, I have a very simple Maven project. If I go to the POM file, I'll need to include the dependency to the latest version of Antler. Just see. Okay, so pretty much I add here a dependency to the latest version of Antler 4, which is 4.7.1. And then in source main Antler 4, I add my Java lexer and parser. In that particular case, I have my grammar for parsing Java 20 source code. One of the drawbacks of Antler is that The grammar definitions lag slightly behind the newest versions that they release of the Java platform. So for now, we don't, for example, have a way to parse Java 21. If you want to do that, you need to customize the grammar or wait for a newer version of the grammar to be implemented. So we add the dependency, we put the grammar definition, and we create a very simple method. So in our main method, the source code I would like to parse is a simple class called example with one function inside which returns x plus 10. So to do that, I initialize my lexer first. Then from that lexer, I create a command token stream, and I pass that command token stream to my parser, which I initialize. Then from the parser, I say parser.compilation unit, which returns the parse tree that Antler generated from the generated parser. I create a parse tree walker, and I pass to this walker a custom expression listener. So my expression listener is something that I write. So whenever I reach an expression in my parse tree, I just print out what is that expression. In the particular case of my class, I just have one expression, which is x plus 10 in the source code. So if we run this, we can see that we just print the expression out of the source code. Very, very simple example, but it illustrates how you can start using Antler and do way more complex things. Pretty much similar thing if we want to use JavaCC, for example. Again, we need to put in the source main JavaCC the proper grammar. If I open the grammar that JavaCC supplies for parsing Java, you can see it's like almost 6,000 lines of code compared to the Java parser of Antler, which is about 4 times less. So it's way more verbose. So I put here the grammar. In my POM file, I also include the dependency to JavaCC, latest available version, which was released some months ago. And what I can do, again, I create the very same example class with one function that returns x plus 10. I create a class generated JavaParser token manager. In that particular case, I print out the next token that gets parsed by the generated parser. So if I run this, it starts parsing the class, and it returns first the public modifier, then class, example, and so on and so forth. In that particular case, I'm not using a listener. I'm just iterating over what's been parsed by the parser that's generated by JavaCC. So this is how we can, let's say, quick start using Antler or JavaCC. However, if you want to really analyze more easily Java source code, parser generators and peg parsers, as I mentioned, are quite generic. And they also may not be very up to date with the latest language version that you would like to analyze. So for that reason, more specialized parsing libraries exist specifically for Java code, like JavaParser and Eclipse JDT, and others which are not so well supported, like Spoon. So let's look specifically at JavaParser and Eclipse JDT. JavaParser is a Java library which is currently actively being developed, which is based on the JavaCC parser generator. It provides support for JDK 21, and it also generates abstract syntax tree from a piece of Java code. It provides extra capabilities for source code analysis, like you can write a form of queries, DSL-based queries, to analyze the abstract syntax tree. You can also attach listeners to listen for events during the parsing process. So there are different ways you can use to analyze the generated abstract syntax tree. And yeah, some of the main capabilities are, like, for example, query methods. For example, give me all the methods in a particular class, or give me all the expressions that satisfy certain criteria in the abstract syntax tree. So you can think of the library like providing SQL-like capabilities for your analyzed source code. It also provides you with the capability to generate code. So you analyze your source code as an IST, you do some transformations, and you can generate back Java code from that IST. So it also provides generation capabilities. It also provides a way to modify the generated IST. And it also provides additional capabilities like, for example, more enhanced symbol resolution. So it's not only sufficient to see that we have an expression like x multiplied by 10, but you want to get more information about x. What type of variable is that? Is it like a static variable? Is it like a local method variable? And things like that. This is some additional symbol resolution that's provided by the library out of the box. To parse a Java source file with JavaParser, it can be as simple as calling the static parse method from the static JavaParser class, and you supply, for example, a file with your source code. And that generates a compilation unit instance. On the other hand, you have another even more powerful library, which is called Eclipse JDT, or Java Development Tools, that you can use as an alternative to JavaParser. In earlier days of the Eclipse development environment, it was quite hard to use Eclipse JDT out of the box because you need to drag a lot of dependencies from the Eclipse framework, like some UI components and stuff like that. But in the latest versions of Eclipse, they've put some effort to extract that as a separate Maven dependencies, a single separate Maven dependency. So you can more easily use Eclipse JDT without dragging too much dependencies in your project. And it also supports JDK 21. It's actively developed and maintained along with the Eclipse distributions because Eclipse JDT is the main parsing library used in the Eclipse environment to analyze source code, and at the same time, it provides more advanced capabilities like code completion or partial compilation. For example, if your source file doesn't compile, it can still generate abstract syntax tree from that partially compiling source code. So as you can see, it provides, in some cases, more advanced symbol resolution than the JavaParser library. But that comes at the cost of more complex starts. So it's more difficult to start using Eclipse JDT than JavaParser library. Eclipse JDT provides things like, for example, visitors for AST nodes through the so-called AST visitor class, where you can attach different visitors during the parsing process. It also provides rewriting of AST nodes, so you can directly rewrite the abstract syntax tree or using an instance of the AST rewrite class. As I mentioned, it provides more advanced capabilities for code completion and content assist capabilities. Typically, Eclipse JDT is modified to be used in environments like a development environment like the Eclipse IDE. But at the same time, you can use it for advanced code analysis. And to get started with Eclipse JDT, what you can do, we can read a file as a string. This is what the first line is doing. Then we create a new document instance from our string source code. And then we create an AST parser by calling the static new parser method. And in that new parser method, we specify what version of the Java language specification do we use. In that particular case, we would like to parse Java 21 source code. And then we set the source code to the parser. We call parser set source, document get to char array. And then from that parser, we call the create AST method that creates an abstract syntax tree. The root of that abstract syntax tree is the compilation unit instance. And that instance, we can use it to make whatever we want with the abstract syntax tree, to generate, to modify certain nodes, to extract some metrics, and whatnot. There are other libraries which are less maintained and developed than JavaParser and Eclipse JDT, like Spoon. It evolved as a project on top of Eclipse JDT. It was developed at the time where it was quite harder to use Eclipse JDT than it is now. And it aimed to simplify the use of the Eclipse abstract syntax tree. In that manner, the Spoon-generated abstract syntax tree is simpler to use than the Eclipse one, and it provides additional capabilities for traversal and symbol resolution of the syntax tree. It provides also a lot of extra capabilities like patterns and matches for advanced code querying. It provides additional capabilities for code transformation and generation. It provides something that the other libraries don't provide, which is JavaDoc parsing, because JavaDoc on its own provides separate definition language that we might want for some reason to analyze. So as part of our framework, we would like, for example, to do some additional analysis on JavaDoc. And this framework provides these capabilities. So let's see how these frameworks work. So to get started, what we are going to do, in source main resources, I'm going to have a multi-set class, which implements the Java util set interface. It represents a set-like data structure that allows us to keep multiple copies of the same element. Most of you know what multi-set is. It provides some methods like return the size of the multi-set, check whether the multi-set is empty, and so on and so forth. In particular, we also add a method which is, I added a custom method which is called create thread pool, which has certain specifics. So the first thing I would like to do is, let's say, something simple as counting how many methods my class has. First, if we look at how JavaParser does it, so what we do, we get a URL to that Java source file. We create a new file instance, and first thing we do is count the number of methods. How we do that? So we create a compilation unit, which represents our abstract syntax tree. Then we call the findAll method that passing a method declaration class, which finds all the method declarations in that compilation unit. This compilation unit corresponds to the multi-set class that I have, and it just counts them. It's as simple as that. If I run this example, we'll see that we have 20 methods in our class. As simple as that. In that manner, if you can derive way more complex metrics, for example, from your source code. So this is a simple use case of how you can build something very simple to calculate metrics, for example. If we want to achieve the same things with JDT, again, we get a URL to our static resource, which is our Java file. And we do the same thing. So how we do it with JDT, the code is slightly more. So we create a document, then we create an AST parser for Java 21 source file. We create a compilation unit from the parser that we have. And the way we query here the compilation unit is that we get all the types, we iterate over them. First, we check that the note is a type declaration, so we get the class note in our abstract syntax tree. And then we get the body declarations, which returns all the bodies that we have in that class file. This might not only be methods, this might be static blocks, init blocks, and so on. And we check if the body declaration corresponds to a method declaration, we increase the count. This is how, with JDT, alternatively, we find the number of methods in the Java source file. If we run this example, we'll see that, without any surprise, the result is exactly the same. So we can do something more interesting. So for example, let's say we would like to do some check for bad patterns in our code. If we open the multi-set class, you can see that intentionally I used capital letter for the method naming, which is for sure a bad practice. So I would like to check that in my source code I don't have, for example, bad method names. How we can do that? So with JavaParser, I've created another method for the purpose called check method, bad method names. Again, I create a compilation unit from my source file. I find all the method declarations, and I check if the method name is starting with an uppercase. And if that's the case, it says bad method name and prints the name of the method, which is not correct. If I run this example, I can see that with JavaParser, I discover one method with bad method name, which is called create thread pool, because it doesn't start lowercase. I can do the same thing, as you might guess, with JDT. And as you can see, the main point is it's not really complex to achieve that. So it's a bit more code to bootstrap and generate the Java parser here, as we saw in the previous example. Again, we find the node that corresponds to the class, which is a type declaration. We get all the body declarations in that class, and for all the method declarations, we get the name of the method, and we check if that method name is uppercase, for example. If that's the case, then we print that the method name is not correct. Pretty much as you can expect, the same result. And of course, you can do way more complex things. So we can, for example, if we want to check that we validate, for example, the parameters for null pointer in our methods. So here, for example, if I go back to the multiset class, we want to check that the count parameter that we supply to the method is not null. We want to explicitly make sure that we have a null pointer check in our method. How we can do that? So with JavaParser, again, I create a method check parameter validations. It's a bit more complex, but again, I get all the method declarations. I get the parameters, and I check if the parameter is not a primitive type. I would like to check for null pointer for non-primitive types. I get the parameter name, and then I get all the if statements in my method. I find all the if statements. I get the condition of that if statement, and I check if that expression is a binary expression, which is an equals expression. And I check that the left side of the expression is the parameter name, and the right side of the expression is null. So let's see if I run now this, let's see if I'll find something. Failed to retrieve null check for parameter count. So it scans all the methods, and it doesn't find null check. Now, if I add such a null check here, if count equals null, then we return null. Very standard thing. And run again the example. So now the error message is gone, so we are able to discover null check for our method, because we added that. If we want to achieve the same with Eclipse JDT, let's look at quickly how this can be done. So again, we get the method declaration node. We get the methods. We get the parameters of that method. And then for each parameter, we do pretty much the same thing. So we check that it's not a primitive type parameter. We create a null check visitor, and we call method accept visitor. In that particular case, I use the visitors provided by Eclipse JDT to make that null pointer check. If I go to that visitor, there is a visit method that gets executed when we reach an if statement in the generated AST. And if it's an if expression, we check the conditions, whether this is an equals if expression, and whether the left side is equal to the parameter name that we supply, and the right side is null. Pretty much similar thing like what we did with JavaParser. And if we run that, as you can expect, it won't discover that the count method is not having a null check. So it does the same thing as pretty much what the JavaParser library is doing. And these relatively simple examples really demonstrated how we can start building a tool for static code analysis, in particular for Java applications, but you can use the same approach to build a tool for any other type of language. You just need to find the proper library that provides similar capabilities to what we saw. I think we have 1 minute for any questions. Are there any questions? No?
If not in person, I think there's one in the Huva app, so I'll just read it quickly.
Okay.
Actually, there's two, so which one do you want?
Let's start with the first one.
Okay. What are the potential use cases where a parser can be effectively applied?
As I mentioned at the beginning of the session, it can be multiple use cases, so depending on what you want to achieve. It can be as simple as getting source code metrics. but it can be way more complex as willing to rewrite the source code. So for example, you want to do some automated refactorings. And this is entirely possible with the frameworks that we saw.
Cool. And one more is, did you have a chance to integrate a custom parser into a CI/CD pipeline? If yes, can you share the example?
A custom parser. To be honest, I didn't have such a use case. It's mostly that I use this library, and in simpler cases, for example, just regular expressions if you want to build a simpler DSL, not necessary to analyze any full-blown programming language. But yeah, I mean, I guess it's the same for everybody in this room. Most of us use mostly regular expressions to do more basic parsing capabilities. But if you want really to do more complex analysis, you can go with the approaches that I demonstrated.
Great, thank you.
All right, so thank you, everyone.